Hello and welcome back. Today we're doing random forests in R. As a reminder, there are 3 advantages to random forests. They detect interactions, they detect nonlinearities, and they naturally cross-validate. But they are not transportable. GLMs are. And GLMs fit, but they are transportable. So why not combine the strengths of both approaches? And that's what I'm going to show you today in R. But first, let me talk about my general strategy. We're going to use random forest with its variable importance measures to find a set of plausible predictors. And when we visualize these predictors, they will tell us whether we need to include interactions or nonlinear terms. And then what we're gonna do is we're gonna use the general linear model to then fit a model based on the visual of the random forest model. And we may need to add nonlinear terms, or we might need to add interactions. So with that, let's get to R. Welcome to R. Okay, so we're gonna start with requiring, or you could also go library, does the same thing, but that basically loads the party package. And I don't remember what party stands for. It's like partitioning, recursive, something, I don't know. Anyway, but it's used for making decision trees and that sort of thing. And of course we're going to require flexplot. And now I've also made comments in this. I will be sure to include a link to this file in the comments so you can follow along as you wish. So we're going to set a seed. What does that mean? Well, when you're doing random forests, remember it is randomly sampling variables and is randomly sampling observations. And because it is doing it at random, the answers by nature are not reproducible. But what you can do is you can set the seed, and basically what that does is that the random numbers that are generated in this instance are going to be consistent. And so if you choose set.seed and put the number to 1010 like I did, then your results will be identical to mine, assuming you're using the same version of R as I am. I heard rumors that they changed how the seeds operate. Anyway, they should be similar even if they're not perfect. But if you want to try to get them exactly the same as mine, then set it to 1010. So the data set I'm going to use is Avengers, and because I'm lazy, I'm going to go D equals Avengers, so I don't have to type in Avengers every time I want to reference my data set. And again, I have comments in here, so the function we're going to use is cforest. And if you want to learn more information about what arguments are allowed in cforest, you could always type, like it says right there, question mark and then cforest, and that'll bring up the documentation. And so what I am doing is I'm going PTSD tilde dot. And what does that mean? Basically that says I want to predict PTSD with every single variable in the data set. That's what the dot means. And so if I run this model, it's actually going to take quite a while to run. Well, actually, I guess it wasn't that bad. It only took me, 2 seconds-ish. But later I'm going to show you how to visualize these. Do not visualize this model. I repeat, do not visualize this model. It will take forever. And you don't need to know why, but if you are interested, the reason why is because when you use the visualize function in the background, it is coming up with unique values for every single variable and pairing them with every other unique value of every other variable. And so if you've got 5 unique values for one variable and 5 for another, that's going to do 5 times 5 different combinations. So that's 25. Not a big deal if you only got 2 variables. But if you've got 50 variables and instead of doing 5, you do 50, I think is the default, then that's going to be 50 to the, well, if you have 10 variables, that's 50 to the 10th power. That's a lot. That is a lot. So you don't want to do that. So don't visualize that one. So instead what I recommend is you run the model with everything and then you look at the estimates. And this too will take a little bit of time, but not as much as if you were to visualize it. And there we go. I'm going to make this bigger so we can, and then I'll run it again. For some reason, I wish it would automatically adjust, but it doesn't. So it gives you, like I said in the video, there are really 2 metrics that we are interested in. One is the out-of-bag performance, and the other is the variable importance. So let me spend some time interpreting these because they are a little confusing just because of how random forest works. So remember, out-of-bag means the observations that were not used to fit the model, And so what this tells you is it is the quantiles of the absolute value of out-of-bag performance. And so what it's doing is this basically taking the predicted score for each individual and subtracting from that the actual score. And then it's taken the absolute value of that. And again, the predicted is the out-of-bag prediction. So every person has a predicted out-of-bag score. It is going to take that and then subtract from it the actual score. And this right here tells you the quantiles. So the minimum difference between predicted and actual is 0.001. And not surprisingly, the 0 quantile is usually pretty close to 0. 25th percentile is 0.117. The median, or you can think of it as the average. So on average, the difference between your actual score and your predicted score is about 0.263. Now this is a PTSD score. Let's go ahead. I don't remember. So we got to think about what this means on the metric of the variable. So if we go flexplot, PTSD tilde 1, not 2, data equals Avengers, just so we can get an idea of the scale of this variable. Okay, so this ranges from 2 to 6 mostly, and you got some deviation. And so what is this saying? This is saying that on average, on a scale from about, what was it, 1 to 4, 1 to 6? On a scale of about 1 to 6, we are off on average by 0.26. So that's respectable. It's not super impressive, but it's respectable. Maybe someday I'll include standardized differences so you can interpret those in terms of standard deviations. But for now, this will work. And then the maximum difference is 3. So on a scale of 1 to 6, the maximum deviation between what is predicted and the actual score is about half that. So that's a pretty severe departure. But if you look at the 75th percentile, 75% of the scores are within half a point. So that's doing pretty good. Out-of-bag performance actually makes more sense, or it's easier to interpret when we have a binary outcome. And maybe I'll show you how to do a binary outcome eventually. And then after that, we got the variable importance measures. So what is this? And again, when you're using regression for random forest, when you have a continuous outcome or a numeric outcome, it's not as intuitive as when you have a binary outcome. And so what is this? This is the root mean squared error of predicted versus permuted. Now remember, when we're computing out of bag error, remember we are taking the predicted values that the random forest model predicted, and then we're shuffling everybody's score. And so what this represents, basically it's the average deviation from what was originally predicted versus the permuted prediction. And so on average, in our scale of, what was that? PTSD, shots taken seemed to be the most important variable, and it was off by about 0.26 points. So not a huge difference, but it's the best we got. And then we got agility that is off by about 0.257, injuries, north, south, etc. Onto died is NaN, not a number. So I'm not quite sure why that happens, but whatever. It's not that important right now. So this tells us if we were to include everything in the model, these are the best predictors in order, and notice that they're sorted. So the most important predictor is shots taken, then agility, then injuries, etc. Remember, we don't want to visualize that entire model. So now what I'm going to do is I'm going to actually take the top 4 variables and create a new model. Why am I taking the top 4? Because flexplot can only visualize 4 variables at a time. That's really the only reason. And I'll show you here in a minute what happens when we only take the top 4 and whether we know we need to go more than 4 or not. So now I'm going to fit a new model with, it looks like last time I ran it, it had a slightly different model. I might not have set the seed before that. Anyway, so we're going to just take them in order. Shots.taken plus agility plus injuries plus, is north south next? So now that is fitting a much smaller model. Why are we fitting a much smaller model? We're doing that because we know we're going to really struggle visualizing it if we take the entire model. It's also going to struggle if it's only 4 variables, but much less so than it would otherwise. And then we can go ahead and again look at the estimates if we wanted. And so sometimes the estimates can be different, sometimes they're pretty much the same. So before we had shots taken at 0.26, now this time around it's 0.26 again, but notice the order of importance changed. And that's to be expected because the original model that had all those variables, it's trying to account for any sort of correlation it shares with all these other variables. Now it's only concerned about 4 variables. Okay, so we have the estimates, things are looking good, and actually look at that. So our prediction actually improved slightly. So the worst before was 3.23 and now it's 2.916. So apparently having so many variables before might have confused it, but then again, the other ones don't look all that different, so maybe that's just a trivial difference. Now, what we could do at this point is we could use the flexplot visualize function, and that would be fine, except what it's going to do is it's going to choose for you. Let me put this on separate lines just so you can see it all at once. What it's going to do is it's going to choose which variables go where, and you may want to look at it from different angles, and if you wanted to look at it from different angles, you would have to rerun visualize lots and lots of different times. And what's happening in the background is visualize is generating different predictions for different levels of shots taken, agility, injuries, north, south, etc. So it probably is going to take about 5 seconds every time you do that, maybe 10 seconds. And I'm a little impatient, so rather than doing visualize for every different view that I might look at the data, instead I'm going to go down here and I'm going to use the compare fits function. And what I'm going to do is there's this little known argument where you can tell it to return the predictions. And so I'm going to go ahead and run that. Oh, it gave me an error. That's right. So remember before I ran it and it was a different seed, so now it's choosing different variables. And so I'm going to have to put these new variables in. And then I'm going to have to make that a flexplot formula. Well, I don't think it'll matter because we're just generating predictions here. So now if I read that in, that should work. And now it's running. And it looks like it probably took between 5 and 10 seconds, which isn't too bad, but now we have a matrix of predictions. And so if I just, actually I'm gonna go head predictions just to look at the first few. And so notice what it has done is it has taken a bunch of different values of shots taken, a bunch of different values for agility, the different types of north versus south, different numbers of injury, prediction, etc. Actually, prediction is the predicted outcome. Notice that agility is all constant here, and that's because it's going to look at every single unique combination of all the different types of shots taken with all the different types of agility. In fact, if I went to tail, that agility will not be -11 anymore, it'll be 93, which is apparently the maximum that it predicts. But anyway, you get the idea. So it's just generating a bunch of different, it's just sampling a bunch of different values, so now we can visualize it. And so now I have flexplot, and I'm gonna delete, actually I'm gonna copy this line right here, and I'm gonna paste it here, because that is a flexplot formula. So now I'm asking flexplot to look at shots taken, which was that the most important variable? No, it wasn't. Injuries was. Well, usually what I like to do on my first glance of this is I want to look at the least important. And why is that? Because that variable, whatever is put first, is going to be on the x-axis. If this right here has a really strong positive, or even negative, I guess, if it has a really strong relationship with PTSD, then I know that when I initially said just give me 4 variables, we might need to do 5 instead. Hopefully not, and hopefully what we can do is we can visualize that and see that there ain't nothing going on. So, so far this looks like a normal flexplot formula, except now I'm adding the predictions that I had here, and I'm putting them in here. So I'm going prediction equals predictions, and what this is going to do for me is it's going to overlay the fit of the model. All we're looking at is whether these lines are mostly parallel. And if I were to kind of squint my eyes, I see that this one right here, there's a pretty strong difference between south and north. And there is right there. But aside from that, it doesn't look like there's a really strong association between north and south versus PTSD. So I'm not actually too worried about that. So I think I feel comfortable kind of rejecting that. So I'm going to go ahead and take that out now. So now I'm going to put the second weakest predictor, which was, I'm going to have to go up. I don't want to run it again because it'll just, of course, it'll take 2 seconds, which I can't afford the time. So instead, I'm going to spend 5 seconds looking for where I ran it before. That makes perfect sense. Okay. Oh, and I'm looking at the wrong one. So, oh, I was looking at, well, darn, it looks like I screwed things up. And, oh, I just messed up the north-south. Okay, so that needs to be damage resistance. Now, if we look at the estimates, again, that's going to take a little bit of time. Now, let's go ahead and look at this. So, most important is injuries, then shots taken, then agility, then damage resistance. So, now what I'm going to do is in order. So, I'm going to start with damage resistance, put that on the x-axis, and then I will do agility. And basically, I'm trying to either dismiss that variable and say it's really not that important, or what I'm going to do is I'm going to say, oh shoot, damage resistance, that actually has a lot of, it's highly correlated with the outcome, so maybe I ought to go one more variable back. Okay, so now with that, I'm going to again copy this and paste that right there, and then move that plus to vertical pipe, and now I'm going to put damage.resistance there and shots dot taken. Okay, and now if I run this, it'll give me a flex plot that we can now reinterpret. I'm going to zoom in on it. Okay, and again, we're looking for evidence that there is basically no association there, and looks like it's all pretty flat. Maybe there's some curvilinearity there, maybe there's some interactions, but it doesn't look like that strong of a relationship. So, nothing too impressive there, so I feel more comfortable about removing damage resistance. And now, what was the second most important variable? I guess I'll run that again and just wait for my computer to run. Okay, so damage resistance. Next is agility, which is what's there already, so we can just leave that formula as is. In fact, I'm going to go ahead and put shots taken right there just so I know what's next. I'm just modifying the flexplot formula. And then if I visualize that, what do we get? Okay, and so the red line is the random forest model, and there is a little bit of a bend in some areas, not in all areas. So, I don't know, is that worth keeping? Well, for the sake of simplicity, I'm going to say it's not worth keeping. So, let's get rid of that one too. So now we will just do shots taken given injuries. And then let's look at the zoom version of here. Okay, so now we're getting somewhere. So we definitely have a pretty significant slope there. And so now we can start using this to inform what kind of general linear model we're going to use. So to me, it looks like there might be some curvilinearity going on there. So that looks nice. Let's go ahead and look at it from a different view. So I'm just going to copy that and paste it down here, and now just switch the order of that. So now we've got the largest predictor, which was injuries on the x-axis. Looks to be pretty relatively, I mean, I'm kind of surprised that variable is more important because that slope doesn't look as steep. But anyway, between these two plots that I ran here, this tells me that it's possible that there are interaction effects going on. I'm sorry, not interaction effects. There are polynomial terms going on, but probably no interaction effects. Let's go ahead and look at that plot again so you can see why. Oh, yeah, it's already over here. Now this blue line isn't a ghost line. but we can kind of use it like a ghost line and to see if these lines are parallel, and they seem to be pretty parallel. Okay, so if I were to look at this, I would say, all right, Random Forest has been awesome. I thank you, Random Forest, for showing me the wisdom of your massive experience and showing me which variables are actually related to PTSD. And it seems that Random Forest is telling me that injuries and shots taken are two important predictors. And it's possible that there is a curvilinear relationship between shots taken and PTSD, whereas injuries seems to be flatline. So again, Random Forest is great at telling you which variables are important and kind of detecting these wonky relationships, but it's not so good at being transportable. It's not, you can't use an equation in a new data set. You have to keep those 500 or 1,000 trees or whatever. So for that reason, now I'm going to model using GLMs. So I'm going to just fit a model. LM, well, I'll do a full equals LM, and we will do shots.taken. Oh, I need my outcome variable, PTSD tilde shots taken plus injuries. And then I'm going to add the interaction term, because, or not the interaction term, the polynomial term, because this is my full model. So I'll go I shots.taken squared, and then I will go data equals Avengers. So that is my regular old general linear model fit. And now I will do a reduced model, which is going to be that minus the polynomial term. So just get rid of that, and we have our full and reduced model. So now we can go compare.fits, and then we'll just use, we're going to put shots taken on the x-axis because that's the one that had the curvilinear effect. And then we'll go data equals Avengers, and then we're going to compare the full and the reduced. Oh, I forgot to run full. So now if we visualize that and zoom in, just from this small plot, yeah, it looks like ain't nothing going on. Oops. Or I should say it looks like that curvilinear effect didn't do anything. There is no polynomial. Okay, I'll trust you, fine. You're the boss, you win. So we visualized it, and then of course I could do model.comparison and go full reduced. It's totally not necessary because, I saw the plot. I knew that they weren't going to be very different, and of course the Bayes factor, 28 times stronger evidence for the reduced model than the full model, not surprising. So anyway, that's good. So that simplifies things. So what we've basically done here, it's actually really amazing. What we did was we took a data set with lots and lots of variables, and we used Random Forest to figure out, all right, of all these different variables, which ones of these are actually informative. And it helped us use the variable importance to narrow it down to really two variables, shots taken and injuries. And we looked at the Random Forest plots, and they seemed to indicate that we could fit a general linear model, maybe with a polynomial term, but when we fit the polynomial term, it didn't seem to do anything. And so now we have a final model. We used Random Forest to find the variables, and we used GLM to fit a final model. That's cool. So let me do a quick summary of what we've talked about the last couple of videos. With lots of variables, it's very easy to overfit your data. Regression solution, or the general linear model solution, stepwise regression really sucks. Random Forest, on the other hand, is amazing! It's really good at figuring out which variables are most important. So in R, I showed you how to combine the strengths of Random Forest with the strengths of the general linear model. And the end result is we have a good model that doesn't overfit. And we can use that same model and transport it to use it for predictions or whatever. And so let me say one final comment about 4 unique uses of Random Forest models. And again, once I finish my paper, I'm gonna link that in the description because that's basically what that paper's about. One use is for variable selection. Again, that's kind of sort of what it was designed to do. Second is to detect interaction in nonlinear terms. And again, we've already talked about that. Number 3, you can use it for non-parametric modeling. And I've done this a lot. If you've got this wonky curved fit, and a polynomial term doesn't work and you can't figure out what the functional form is, why not use a Random Forest? And then 4, we can use it for prediction and classification. So with that, let's review our learning objectives. Number 1, the general strategy for random forests. Again, we use random forest to find the variables and the functional form of the variables, and we use GLM to then fit the model so it can be transportable. Number 2, how to model random forests in R. Number 3, how to compute variable importance as well as out-of-bag measures of error. Number 4, how to visualize random forest models in flexplot. And then number 6, is that what we're on? The different uses of random forests. Again, variable selection, nonlinear and interaction detection, non-parametric modeling, and prediction and classification. So with that, peace out.